Hello, my name is Mehdi Dust. I have PhD from the University of British Columbia in the field of mechanical engineering. And on today's presentation, I'm going to talk about numerical setup in ANSYS CFX Pre for simulating the pulsatile flow through mechanical heart valve. First of all, you should know that for any kind of CFD simulation, you have to go through some steps. The first step is about the geometry modeling. You can design and model your geometry in any kind of CAD modeling software such as SolidWorks or Unigraphics and import it to the ANSYS design modeler, or you can directly design your geometry in the ANSYS design modeler. On this step, you should notice that you should avoid any kind of sharp edges on the geometry or any small surface or small volumes in order to prevent mesh concentrations around these regions. The next step is mesh generation. On the mesh generation, the mesh again should be suitable for the CFD simulation. For example, close to the surface, you should have very fine mesh in order to be able to capture the boundary layer. For some turbulence modeling, for example, K omega or shear stress transport that are low Reynolds number turbulence modeling, you should use y plus lower than 2 in order to be able to capture the boundary layer into the viscous sump layer. The next step is mesh independency. You should do that in order to be able to have very accurate results. After that, you have numerical setup in CFX Pre, and that I'm going to talk about on today's presentation. Then you have solver and post-processing. First, about the geometry. The geometry that I have chosen is the standard Jude medical valve, as you can see on this picture and here. I have chosen inlet length of 5R and outlet length of 17R. I have to explain for you the different combination of the inlet and outlet boundary condition. As you can see, you have some multiple choices for the inlet and outlet. For example, if we chose the inlet boundary condition, as you can see on here, according to the ANSYS technical notes, the pressure and mass flow boundary condition, as you can see here. In a case that you have reverse flow in the inlet, they are going to put a wall on that region, and in some cases going to make some problems. If you define the velocity specified condition, you can have the reverse flow in the inlet or outlet, but you should have the exact specific profile of the velocity at different times at the inlet or outlet. And therefore the pressure and mass flow conditions are going to result a better physical results. But inlet velocity profile is not usually recommended. For the outlet, again according to this slide, the outlet should be away, far away downstream of the recirculation zone. Because if you, for example, put your outlet boundary condition on here where you have the recirculation zone and some reverse flow in the parts of your outflow, then again you are going to have a problem about the outlet boundary condition. Then you cannot have outlet boundary condition on this line. You should be away from the recirculation zone to prevent such a problem in your outlet boundary condition. Then over here I have chosen 17R away from the from the region of the leaflets in order to have a better result on my CFD study. According to my pilot study that I have done, if I on this combination, if I chose a laminar profile of velocity at the outlet, or turbulent profile of the velocity, or uniform, the result of the velocity flow field around this region are the same. It means that we are far away from these regions and the recirculation zones after the leaflets and the housing. For the inlet, I have chosen pressure inlet. The pressure inlet gives me the opportunity to have the fully developed profile of the velocity downstream over here at the inlet section of the valve. Because I don't know the profile of the velocity at the inlet, this is the best choice. Then the boundary condition is inlet pressure, outlet mass flow rate, or outlet velocity. For the mesh generation, first of all, I have chosen shear stress transport turbulence modeling. This turbulence model is utilizing the K omega and rho Lagrange number regions near the surface and K epsilon at the bulk flow. This specific turbulence modeling is using advanced wall function, but in order to be able to capture the viscous sublayer, you have to choose Y plus lower than 2. I have chosen Y plus of 1. As you can see, it's very fine mesh close to the surface with 12 number of Prim's layer near the wall. For the temporal boundary condition, I have to explain something for you. According to a study, I'm going to show the exact anatomic profile of velocity and flow and pressure. As you can see, at the early systole here, when we have isovolumic contraction, the aortic valve opens and we have the mass flow through aortic valve. It means that the ventricle is contracting and pushing the flow through aortic valve. It goes to the maximum flow and goes down again to 0. And here, at the isovolumic relaxation, we have a small regurgitation flow. It means that we have a reverse flow from aorta to ventricle, left ventricle. I have ignored this part for my simulation because I am concentrating for the analyzing the flow from the mid acceleration to the peak flow, again to mid deceleration. Then I simplified the temporal boundary condition with this condition. As you can see, it starts from 0, goes to the maximum, goes to 0 at the end of systole, and remains 0 for the whole period of diastole. On my next video, I'm going to go directly to the software and explain how to set up the numerical parameters on ANSYS CFX Pre.